My name is Igor Gavrilov, and I would like to present my conception of a dissertation thesis on the subject spatio-temporal statistical analysis, using as an example analysis of road accidents in the Czech Republic and influencing factors. During the presentation, I will talk about the main source of data, provide you with a description of data being used, and the additional source of data taken into account. Then I will outline the case setup factors influencing the number of accidents, and finally I will present you two different solutions for statistical analysis and the resulting conclusion. As a main source of data, I use the Czech Police database from the official open resources. That contains necessary information about more than 1 million accidents taking place in the Czech Republic since 2007. There are more than 30 different parameters in the database, such as the number of cars, injured pedestrians, and, of course, general information of the accidents as such. For each accident, there is the date, time, number of cars, the people involved, and, what is more important, GPS coordinates. On this slide, you can see the number of accidents for the period 2020 to 2023. Looking at the chart, you can notice the unexpected pattern, that the number of accidents happening during the summer season is higher than the number of accidents in winter. The next slide shows the cumulative number of accidents broken down by day of the week. It is obvious that the number of accidents on the weekends is much lower than during working days. There are three categorical regarding the time in the database. The exact time is known, hours and minutes. The time is unknown, and the lack of information on minutes. You can see the distribution on the pie chart. Regarding those accidents where the time is unknown, the probability that the accidents could have happened at another location or another day is very high. Therefore, they will be excluded from the analysis. As an additional source of data, I use the European weather database Copernicus. The database contains information on more than 100 different weather parameters. For the analysis, I decided to use only the 10 most important ones. For example, the temperature, dew point, low cloud cover, snow density, etc. The values for points with distance around 30 km in the database. To obtain weather parameters at the location and at the moment of accident, I created a public API, Application Programming Interface, which is based on interpolating distance weighting, and as a result returns weather parameters at any point at any given coordinates in the Czech Republic for period since 2007. The result from the API can be easily transformed to a data frame in programming language R. So we are moving forward to the proposed solutions. The factors are time, day of the week, months, weather parameters, and binary variable, which represents one of two categories, a workday with a meaning of digit 1 or a holiday digit 0. To create a statistical model, I decided to apply two different solutions, to use polygons and to form clusters. To create a model, it is necessary to group or aggregate accidents. I attempt to group accidents using the nearest neighbor algorithm. However, as there should be a predefined number of clusters, in such case the number could be from 1 to 1.5 million. I took an Uber model as a prototype, but I simplified it according to my needs. And I found a simple solution to divide the territory of Czech Republic in squares with a side of 1000 meters each, and then to arrange accidents into polygons. As a result, I got 79,000 squares that cover all the territory of Czech Republic. As you can see on the next slide, I created a map which clearly shows the most dangerous place are usually located in the city centers. Considering that in the area of 1000 square meters, there can be sectors with greater number of crossroads or potentially dangerous sites, I've usually divided each square into even smaller ones, with side of 500 and 250 meters. The number of different polygons you can see is in the presented table. Here you can see the representative data for polygons with a side of 500 meters and another of 250 meters, where at least one accident took place. After dividing polygons into smaller ones, the quantity of polygons where only one accident happened dramatically increased. On the left graph you can see that the number of polygons of 1000 square meters where only one accident took place is around 8,000. But for the squares of 500 square meters, it is already 27,000. And for those with a side of 250, 71,000. It is important because we need to exclude all the polygons where the number of accidents is smaller than 3. Otherwise, we cannot form the right type of distribution. Look at the following example. I created a model for polygon number 56485. This is a city center where a lot of accidents happened since 2007. The data frame in R was created. That includes such information as date, month, time, day of the week, weather parameters, and number of accidents. As we can see, the histogram, it is similar to a Poisson distribution. On this slide, we can see that the result of our analysis presented in a table with only statistical significant coefficient. Looking at the table, I can say the probability of accident to happen obviously depends on these predictors, month, day of the week, and certain weather parameters. A proposed solution number 1 has a disadvantage of the impossibility of equal division, as the polygons may contain a different number of crossroads or other independent elements. Solution number 2 is based on creating clusters using a density-based algorithm. This is an iterative method, and as an input, we need to have a minimum number of points in a cluster and to know the distance between them. On the left map, there is an example of cluster on a motorway, and on the right map, there is a big cluster in a city street. To use this algorithm, we need to tune in the distance for city roads and motorways. To find an optimal distance, we need to arrange all accidents on the roads and after that to set up a distance for each type of road. For that purpose, I use a transportation network in a vector format. And, of course, GPS coordinates of accidents are not located exactly on vectors. Therefore, the accidents will be arranged according to the distance from the point to the vector. It is complicated, because the calculation must be made not on the plane, but on the spheroid. It is a simple way to create projections of all accidents on the vectors. After forming projections of all accidents, all vectors were split, and I calculated the length of the vector parts. The table includes lengths of the road, directions, and statistical parameters, lower and upper quantile. I defined the dangerous segment as the one with the minimal number of accidents equals 3, and distance between them lower than the upper quantile. And as a result, we can see on the map all highways dangerous segments, and for each one, and a generalized linear model similar to the one presented for the first solution can be created. Here we can see a comparison table for solution number 1 and 2. I have been continuously updating the dataset every month. As for the first solution, it's just arranging accidents into polygons, but for the second, we need to create projections, split vectors, and calculate the upper quantile. As a conclusion, I consider that the both solution will be more precise over time. A density-based algorithm proved to be more applicable for cities, whereas the second solution shows certain great results regarding highways and motorways. Therefore, I believe it would be efficient to create a functional hybrid model.